Welcome back, and you've graduated from intermolecular force boot camp, and good on you. So today what we're going to do, and for the next few videos, we're going to apply those concepts of intermolecular forces to some actual measurable properties of liquids. Today we're going to talk about viscosity, we're going to talk about surface tension, and vapor pressure. Vapor pressure is very important because it determines the boiling point of a liquid, and we'll talk about what the boiling point of a liquid is. So let's go to work right now. Well, howdy everybody, howdy. We're here to talk about properties of liquids. We're in the second section of the 10th chapter of the OpenStax textbook, and we're going along with applying some of these concepts of intermolecular forces. And I'm going to go in the order of the book and briefly talk about viscosity. Viscosity, as it says there, is the resistance to flow. So if something has a high viscosity, or if it's very viscous, like maple syrup, it's going to flow very slowly. And like molasses in January is the old kind of cliche. So now let me explain why that is. Partially that's due to intermolecular forces, because in order for a liquid to flow, these layers of molecules, now they're pretty, close to each other, unlike a gas, they need to flow across each other. They need to shear. And so if there is attraction between molecules that's extremely high, that will cause this substance to become more viscous or have a higher viscosity. Now, that's not the only factor. So the higher the IMF, the higher the intermolecular forces, generally the higher the viscosity. But it's complex because there's also a factor of molecular entanglement. So if I'm just depicting molecules here as spheres, which, as you know, is not the case. You've had Vesper theory. They can have all sorts of shapes. So if you had something that had a lot of branches to it, it would be more viscous. So let's take, for example, motor oil, which has London forces, and of course the grams per mole, the molar mass of the components of motor oil are pretty high, so it has strong London forces. But there's also a lot of molecular entanglement, because if you have little branches sticking out, that will get in the way of this sort of side-by-side motion. So it's a little bit deeper, and that's why I'm not going to talk about it a lot, and I am pretty much done. But we want you to be familiar with the term viscosity, especially you engineers, in the future. Next, I would like to talk about something that is completely related to only intermolecular forces, and that is surface tension. So let's take this little sample of two samples of molecules. Let's say these are water molecules, because water is noted to have a very high surface tension. That's why we can do this demo I'm going to do in just a few moments. That's why a water bug can float on top of water. Now, let's talk about why that is. That is because at the surface of the liquid, or any liquid, you have kind of unidirectional attraction. So you've got this layer of molecules at the top, and it is attracted to everything below and beside it. I'm drawing little arrows there. They'd be double arrows. And so you have this kind of sucking force bringing the other surrounding molecules up, and there's nothing here to counteract that at the surface, which gives the liquid a sort of skin. And surface tension is usually measured in force per linear distance. And so, but in the bulk, you've got this guy right here. Let's be that molecule. And you've got him, or it, being attracted from all directions. And so in the bulk, you would find that water has a density of 1, but at the skin, if you could just measure that small sample of molecules, it's much, much higher. So you would find that water has a very high surface tension because per very small area, you have a great deal of intermolecular force. Mercury, which has something we haven't discussed because it's really not the scope of this course, has very high intermolecular forces, so much that they give it a different classification called metallic forces. So mercury beads like crazy. That's why they used it in gauges for things in the old days. Not good for the environment, so now we don't use it as much anymore. If you had something that sheets, so if you were to spill gasoline on something, it would not bead, it would sheet. That has a very low surface tension. Even something a little bit less than intermolecular force like alcohol would tend to sheet, not bead. So hey, let's give you a little treat here on my kitchen table. You can do this little demo along with me. Let's do a demonstration of surface tension in action. All right, here's a surface tension demonstration you can do at home. This is what we call in science a bowl of water and a paper clip. And I'm going to take these eyebrow pluckers, which are not mine, because I believe that in science, the bushier your eyebrows are, the more believable you are. So I'm trying to cultivate my own. Okay, so what I'm going to do is I'm going to demonstrate this with this paper clip if I do it just right, which I didn't. That's what we call in science failure. If I do it just right. Come on, steady hand, Mike. Yes. There you go. That is an example of surface tension of water at work. And so that's that. You know that stainless steel is more dense than water. Interesting little bit of trivia. This is some liquid soap. I'm going to go ahead and give it a drop or so on the side, not to disturb it. But there. You'll notice that I interrupted the surface tension with that soap. And soap is what you call a surfactant. It'll actually break up the surface tension of things. So there you go. All right. Back to talking about more stuff about liquids. All right. That was kind of cool. Glad you're back. Let's talk about vapor pressure. That's our last concept of the day, but it's going to lead to another thing that's extremely important, and that is the boiling point of a substance. So let's talk about what the vapor pressure of something is. That's supposed to be a drawing of a flask. I know it looks kind of like a gourd, but if I were to take and pump all the air out of that flask and it was a rigid container, and then without letting any air in, inject some liquid. Could be water, could be ethyl alcohol, could be an ether, doesn't matter, it's a liquid. It would not stay there in the liquid phase because it's not opposed by anything, because there's a vacuum in there. You would find that after some time you would establish some molecules in the gas phase, and that there'd be a point where it would just come to rest, and that pressure, you guys all know about pressure, would not change, and that's because the rate of it vaporizing and the rate of it condensing would become equal. And so eventually that vapor pressure would become constant, and we would actually call this, we would call it the equilibrium vapor pressure. All right. And that depends on two factors. How strong the intermolecular forces are. So let's say we're at room temperature and that was water. You would find out that water has a pretty low vapor pressure because it's got such strong intermolecular forces. But if you took another liquid that had weak intermolecular forces, let's say like ether, that would have a very high vapor pressure. So vapor pressure is kind of inversely related to intermolecular forces. And then the only real factor of vapor pressure is how strong are the intermolecular forces and what the temperature is, of course. So if I were to heat this up a little bit, I would populate this with more molecules. And let me show you a little diagram from your book. This one. So this is a plot of number of molecules. Let's call that pressure. And this would be kinetic energy. And you see where it says low T and high T. So let's say that this was room temperature, 25 degrees. And then you go and you jack up the pressure a little bit. Minimum kinetic energy needed to escape. This is intermolecular forces. So that line, if it was water, that line can't move unless you're talking about some other sort of substance. That line is there. For water, it is X. But if you were to heat something up like water, you're going to find that it vaporizes more quickly. And you notice how more molecules are under that, have gone past that line? So we could call this would be the liquid gas line. That is the energy required for vaporization. Let's go even further. Let's say that was 25 degrees and 35 degrees, and then I was going to heat it up even more. Even more of those molecules would be over the line. And so what you're going to find is that vapor pressure, if I was to plot it, would be a curve. It would be, let's make a quick plot here, and I'll try not to mess it up. Let's say that this is vapor, and we're not going to change what the substance is. All right, that's vapor pressure. This is temperature. You'd have this sort of exponential relationship where, you know, at absolute zero would be nothing, but, you know, it would be kind of like this sort of thing. All right? And that's the kind of relationship you have for vapor pressure. It's a curve. Now, I don't want to equation you to death. As a matter of fact, we haven't done any math yet. We're going to do it soon, though. But there's an equation to govern this called the Clausius-Clapeyron equation. You folks who take my course at the college, you're going to do a whole experiment on it. And so what you're going to find out is that really simple mathematics can't describe curves, so we need to throw logarithms in there, and that's why I hope you guys are very versed in logarithms. But here's what I'm going to do here is draw a little line there, because the next thing we're going to do is we're going to define what the boiling point is. Boiling point. You know, we just threw that term around like you knew what it was, and you kind of know what it is. You say, hey, water boils at 100 degrees. But you know what we've never done? We've never really kind of defined what the boiling point is, and that is a temperature. So, for example, water, 100 degrees, all right? At which the vapor pressure, you know what that is now, is equal to, this is important, the surrounding pressure. Now, I don't know where you are right now. I'm in Dayton, Ohio. We're not at 1 atmosphere pressure, folks. So what usually you're quoted is this number here, 100 degrees C. That would be 1 atmosphere. So if you're at sea level with a dry atmosphere, water would boil at 100. Where are we at Dayton, Ohio? It might be slightly lower. When we boil water in the lab, it might be something like 97 degrees, something like that. And so what if you were in Denver, Colorado? You might be way down here because you're a mile high. There's less atmosphere on top of you. I'm not going to commit to saying what the temperature would be, but it might be several degrees below 100. And so what you'll find is if you read the side of a box of mac and cheese, which when I want some light reading, I do that, you'll find that it always says high altitude instructions. And basically the directions just say boil it longer. Because when you boil mac and cheese in Denver, Colorado, it's going to not boil at the same temperature as it is in Dayton, Ohio. It's going to boil much less at a lower temperature. And so that's going to cause you to not cook your macaroni as fast. By the way, why would people eat mac and cheese in Denver, Colorado? Must be they suddenly got hungry for some reason. I don't know why. So anyhow, if we're going to go and look back on our curve, the boiling point is where almost all the molecules are underneath that curve. And so what happens is normally with a liquid, it just happens at the surface. But when it's boiling, now all those molecules, both at the surface and in the bulk, are eligible to vaporize. And so, so that's a little bit about the boiling point. And let me tell you another thing, folks. This is just trivia, and I am not trying to waste your time. If we are in outer space, the pressure in outer space, it's pretty much a vacuum. So if we suddenly were to get sucked out of a spaceship, all the fluids in our body would vaporize and we'd blow up like a balloon and explode. And so what really irks me is when I'm watching a science fiction movie and somebody gets sucked out of a spaceship and then they don't blow up like a balloon. Now, I do got to say, I saw something I was watching The Outer Limits on Thursdays. I don't have cable TV, but I watch Outer Limits through the antenna. And on Outer Limits, a guy got sucked right out of the spaceship and he exploded. And I was like, yeah, that's better. Except guess what? It made a sound. He went, poof, and I was like, oh, you guys could have nailed it. There's no sound at space. Okay, so anyhow, one more thing, folks. Let's compare some different. Now, you have a figure like this in your OpenStax textbook. Those are four different liquids, and their vapor pressure curves and the temperature at which they boil. So there's, let's say this is 1 atmosphere, which is about what, 103 kilopascals. So that's about 1 atmosphere. There's 100 degrees C. That's the normal boiling point of water. It's like 79.5. That's the normal boiling point of ethanol, which has only one OH bond and is a little heavier, but its London forces aren't enough to make it as strong of intermolecular forces as water, which is nothing but polar bonds. So there's a lot of non-polar bonds in ethanol. We were talking about ether a few times ago when we were talking about polar bonds, a couple videos ago. I don't know, I think 38 degrees. So check this out. If you're at room temperature, here's room temperature, 25. Ether is almost boiling. It's pretty close to boiling at room temperature, and that's why ether is so dangerous. We use it in an organic chemistry lab. If you spill it, it vaporizes. Now, the vapor stuff burns really good, so if you spill that and then there's a flame nearby, you're going to have a cloud of, not cloud, but you're going to have all this vapor. So ether is very dangerous. It can cause a flash fire for that reason. But intermolecular force is stronger, somewhere in the middle, weaker. How about this guy? Ethylene glycol is what they use in antifreeze. And when we talk about the solutions and their boiling points are higher usually, this thing, ethylene glycol, if you look at it, it's got 2 OHs, just like water has 2 OHs, but it's heavy. And so it's got a very low vapor pressure. And you see that by the curve. It would take a long time for ethylene glycol to boil. So there's some vapor pressure curves, and that's going to gear us up for next time. I know this video was a little longer than normal, but next time we're going to talk about the journey of something as it vaporizes. Actually, we're gonna tell a story of an ice cube and its journey through temperature. So tune in then. All right, folks. Thanks for listening, and you'll never look at a science fiction movie the same if a guy gets sucked out of a spaceship. See ya. Peace. Bye. Salutations. So long.